All right, let's go ahead and get started. So, I hope everybody is doing okay and staying safe during this quarantine and doing all the things you need to do to keep up to date with your classes because we do need to get back into a routine, not exactly the same routine, but a routine for our classes. So, let's bring up. Okay. And let me just move this canvas back over. So, some things to note before we get started here. Like the note says down at the bottom there is up to a 40-second delay on the stream here. It just takes some time for the information coming from my computer to get to yours, and then from your computer to get to mine. So just keep that in mind when you ask any questions or have any comments. And I will try to answer anything that you might ask me as soon as possible. But again, there will be some delay, so just be patient. So let's go ahead and get into our lesson. So, like I have mentioned in the past, we have several different ideas in algebra. Of course, two big ideas are the difference between expressions and equations. So, we've said in the past that expressions are things like 2x, and I am using a tablet. It's not the easiest thing to use, so bear with me. So 2x plus 7. It's kind of stretching everything that I write. And so this would be an expression. It represents a single value. We don't know what that value is unless we have something to plug in for x, but it represents a single idea. This is opposite from an equation where we might, add something in like equals, 4. Okay? So an equation takes two expressions, two single values. So 2x plus 7 is a single value, 4 is a single value, and it compares them. And the comparison that it's making right now is that both of these values are exactly equal to each other. And it's kind of testing to see if that is correct. So, could this work, is what it's saying. Could we have 2x plus 7 equal to 4? What's going to be necessary for us to make this true? That's the x statement. X is going to be what we use to make this thing true. So when we were working with expressions, there was basically only one thing that we could do with that, and that is to simplify it. If we can combine like terms, multiply anything, factor anything if we want to, simplify. With equations, we can solve them, and solving means that we're going to take the information given to us in both of these expressions, both sides of the equation, and try to manipulate it so that we only have x by itself. Again, x is going to be telling us what we need to have in order for this thing to be true. So we can do that by moving things around. So the first thing that I want to do is I want to say, all right, if I want to get x by itself, I need to eliminate the other numbers on this side. I need to get rid of the plus 7 and the times 2. And I'm going to want to tackle this kind of in reverse order of PEMDAS or GEMS. So the last thing that we do in GEMS is add and subtract. So I'm going to get rid of any kind of added or subtract by doing the opposite. So if I have plus 7 here, I'm going to subtract 7. And I'm also going to do that to this side because what this equation shows, again, is that these are both exactly equal. In other words, they have balance. Both of these should be equal. They should be balanced with each other. And to preserve that balance, we need to do the same thing to this side that we did to this side. So here, plus 7 and minus 7 Those cancel. They're gone. And we are just left with 2x. On this side, when we subtract the 7, we actually have something that's going to come out of that. So let's see. 4 minus 7. It's going to be negative 3. Okay, so this represents the exact same thing that we had before, just written in a different way. We have moved this value over to this side by kind of manipulating the balance between these two ideas. We can keep on doing this again until we get the x value by itself. So what we'll do is we will divide by 2, since what we're doing right now is multiplying 2. If we divide by 2, again, that will cancel this. And we do the same thing to this side. Divide by 2. So again, that cancels there. We are left with x on this side. And that is equal to negative 3 over 2. So again, the original equation that we had, 2x plus 7 equals 4. What this was doing was comparing these two expressions, 2x plus 7, comparing it to 4, and saying that they're exactly equal, that they're exactly balanced. And what would we have to plug in for x for this to be true? Well, by working through this, what we've seen is that we need to plug in negative 3/2 in order for this to be true up here. So this would be our solution. Let me try that again. So that would be our solution. Now, another way of saying this is that this would be our condition, because this type of equation is called a conditional equation. In fact, there are 3 types of equations out there. The first type, like we're seeing here, is the type that we're used to seeing all the time. We move things around, we get x by itself, and we get some kind of value out. It's a condition. It is what makes this thing true. It is the condition that makes it right. So, again, that is called a conditional equation. Okay. So, if we have conditional equations, do we have other types? Well, yeah, like I said, there's 3 types of equations out there. So, conditional, it's the one that's normal. We're used to seeing it. Nothing strange going on here. Let's go ahead and quickly have a few more of these conditional equations just for practice before we get to the others, though. So I'll go ahead and clear this off. And remember that if you ever want to go back to any of these, you can just come back to this channel. They will be archived. All the videos will be there, and you can go back through them. As well, if you miss a class, you can go back into the channel and get the video. So it's probably a good idea to subscribe to this channel as well. Okay, so like I said, let's go back and let's look at another conditional equation. A little bit more complicated this time. My first expression is going to be 2 times 4z minus 7 and then we're going to set this equal to another expression. Like I said, there are always 2 expressions that we're comparing to each other, and this other expression is going to be negative 9 times 5 minus z. Let's try that again. Again, sorry for the terrible handwriting. This tablet is not easy to use. Okay, so like I said before, we have two expressions and we're comparing them. And the equal signs between them means that we are saying that they are perfectly balanced. They are exactly equal to each other. Now, they're only going to be equal to each other if we have a particular value for z. So, let's see what we can get out for it. Now, the first thing we need to do, though, is say, all right, if we're going to start moving things around, how are we going to do that here? We have parentheses. Those parentheses are grouping those numbers together and kind of locking them in place. They're not able to move around as they are right now. So before we can start moving things around, we actually have to simplify these expressions. So like I said again, if we have expressions, the really only thing we can do with them is simplify them. In an equation, we still might have to simplify them if we want to start moving numbers around. So let's go ahead and simplify. Of course, the way to do that here is to distribute. So I've got 2 times 4z minus 7. I'm going to need to distribute this 2 into the parentheses. So 2 times 4z, it's going to be 8z. Then 2 times negative 7 is going to be negative 14. Okay, so don't need the parentheses there anymore because the number that was outside here has gone inside. Parentheses are gone. These numbers are kind of now unlocked. We can work with them. Need to do the same thing over here though. So distribute the negative 9 into our parentheses. So negative 9 times 5, that's going to give us negative 45. And then negative 9 times negative z is going to be positive, because negative times a negative is a positive, positive 9z. Okay. So, again, what this has allowed us to do is get rid of those parentheses and unlock these numbers. We can now move them around. Now that each of these expressions is simplified, we can start moving things around. And that's always what you want to do. You want to make sure that your expressions are simplified before you start trying to solve. So, now we want to actually go ahead and do that. We want to try and solve. So what are we going to do? We have z on two sides. Before we only had a single z and it was on one side. And we could just take things away from it to get it by itself. Well, now because we have z on each side, this variable on each side, what we're going to have to do is choose a side to put it on. We can have it on the left side, we can have it on the right side, and it really doesn't matter. So if we want to move like the 9z over here, that's fine. If we want to move the 8z over here, that is also fine. The end goal, though, is still to get everything to one side and have z by itself. So we need to keep that in mind. What's going to be easiest to do? What's going to be the easiest way to have this solved if we have z on one side or the other? Well, I honestly feel like having an 8z go to this side would be easier. If you don't agree with me, if you feel like it'd be easier to take 9z to this side, go for it. It does not matter. So, again, we need to get the z's together. So I'm going to subtract 8z, subtract 8z, again, preserve balance on both sides. So this cancels here, and here we now have 9z minus 8z. Well, 9 minus 8, that's 1 left over, so a single z. So on this side we have 14 left, negative 14. On this side we have negative 45, then plus the 1z left over. Okay. So again, we want to get z by itself, so the only thing left here that's keeping it from being by itself is this negative 45. So we're going to need to take negative 45 to this side. All right, so we're going to add 45, add 45. Again, keep that balance. Make sure it's always the same thing on both sides. And it cancels there. And then on the other side, we essentially have 45 minus 14. That's going to give us 31 left over. So we have 31 equals z. And there is our solution. Again, there's our condition. The thing that makes this original equation true, the thing that makes this work, is as long as we plug in 31 for z in both of these z's. Okay, so I will pause here for a minute in case we have any questions. Again, remember that there is a delay, so I'll give us some time to get those questions up here. Okay, I'm not seeing any questions, so I will move on. However, if you do come up with a question, just type it in, let me know, and I'll go back. So I'll save this. Okay. So again, as I said before, there are three types of equations. The two that we've seen so far are conditional equations. Again, what that means is... Oops. There we go. What that means is that there is some condition, in this case 31 equals z, that makes this thing true, that makes it work. Now with the other two, the things that we get when we solve these equations are going to be a little bit different. They're going to show us something that we're probably not used to seeing. So let's have a look. So this new equation, the first half is 5x plus 12. So 5x plus 12. Let me try that again. Plus 12. There we go. And it's equal to... the other half is 5 times x plus 3 minus 3. So 5 times x plus 3 minus 3. Okay, so this looks like just a normal equation. It doesn't look any different from what we've been working with so far. We've got x on both sides. We've got expressions, nothing strange going on so far. However, again, we will see that something interesting is going to happen here. So let's see what happens when we start to solve this. All right, well, first things first, we've got an expression here on this side that needs to be simplified. We have these parentheses here. We need to break those parentheses open to get these values out. So we're going to need to distribute 5 into the parentheses. Okay, so this side, nothing happens. It's still 5x plus 12. We haven't done anything over here. This side, again, we distribute that 5 in there, and now we have 5x plus 15 minus 3. Okay. Well, we can actually further simplify this by combining like terms. If you look, we have 15 and negative 3. Those are like terms. We can combine them. So if we combine those, we have 5x plus 15. I'm sorry, plus 12. Because 15 minus 3 is 12. Well, that's interesting, because our other expression was already 5x plus 12. So now what we have, since we've simplified down to this point, is 5x plus 12 equals 5x plus 12. I mean, that makes sense. That's how it should be. They should be exactly equal to each other, but in this case, they are exactly the same. And this is where you should start thinking, okay, I have a different type of equation here. This is a surefire way to tell that you have what's called an identity. Oh my goodness, that is the worst handwriting I've ever seen. Okay, so in an identity, what happens is we have some value equal to the exact same value. And if we were to continue to solve this, so move things around until we get x by itself. So let's see. Minus 12 to this side. Minus 12. That cancels there, but it also cancels here, leaving us with 5x equals 5x. Again, same thing. So we want to get x to this side. We want the x's to be on the same side, so we will subtract 5x, subtract 5x, cancels on this side, also cancels on this side. So all that's left over here when we cancel that is 0. And it's the same thing here. These canceled, so all that's left over is 0. Meaning 0 equals 0. Well, again, that makes sense. 0 should be equal to 0, but where's the x? Well, x canceled itself out, meaning that x actually does not matter in this equation. It doesn't need to be there, really. Another way of looking at this is that we could plug in anything for x, and it would work. Any real number. In fact, that is what we say is the solution for this, is that x equals all real numbers, or we have this symbol for that called all reals. It's like a double R looking symbol. Okay, so again, this is called an identity. Identities look like any other equation. There's nothing weird going on here until we solve it. But the way that you know you have an identity is if you have some value exactly equal to the exact same value. So like we had before, 5x plus 12 equals 5x plus 12. Or if you want to simplify it all the way down, 0 equals 0. So if you have something like that, 0 equals 0, 1 equals 1, x equals x, anything like that, it's an identity, and your answer is that x equals all real numbers. It does not matter what we plug in for x. It's always going to work. Now, these are actually kind of useful because in algebra, sometimes we like to test and see if things are related. So we could come up with two different ideas and compare them using the equal signs and say, all right, are these things equal? Are they the same? Are they actually the same idea, just written a different way? And if they come out to be an identity, then indeed the two things that we were comparing are the same thing. And that's how we write proofs. That's how we prove that certain things in algebra work all the time. And it's through these identity things. Okay. So let me save that. Go to a new one. And I'll give us a little bit of time to asking questions on that one. I know that identities might be a new idea. Okay, I don't see any questions, so I'll move on. So, again, three types. We've looked at conditionals, which says that sometimes it'll work, sometimes this idea, this equation will work, but we have to have a particular value for x to make it work. We have identities, which say x doesn't really matter. We can put whatever we want in there and it'll work. These two things are essentially the same, just written a different way. Third, we have this type of equation. So I'll start out with 2 times x minus 6. And it'll be equal to negative 5x minus 12 plus 7x. Was that minus 12? Yeah, minus 12. Okay. Excuse me. So, again, doesn't really look strange. Looks pretty much like a normal equation. However, like I said before, this one's going to be kind of different. It's going to come out to be something maybe we haven't seen before. And it's only going to be once we start solving it that we start to see the differences come out. So let's see, what do we need to do? Well, we've got parentheses on this side. So we're going to need to distribute this in order to simplify this expression. We've also got like terms on this side. So we're going to need to combine our like terms on this side, negative 5x and positive 7x, in order to simplify this. So let's go ahead and just do that all in one step. So 2 times x is 2x. 2 times negative 6 is negative 12. Then we have, again, the negative 5x and the positive 7x. If we combine those, we get positive 2x. Somebody tricked me on this one. Let me change one thing here. Make that positive 12. Okay. So 2x plus 12. Okay. So now if we look at this one, we have 2x minus 12 is equal to 2x plus 12. That doesn't make any sense. We can't have subtracting 12 be the same thing as adding 12. This can't possibly be true. It does not make any kind of sense at all. So this is our kind of a clue that something weird is going on here. This is our third type of equation. This is a contradiction. So a contradiction is something that cannot possibly happen. So if we go ahead and keep solving this, we would add 12 to both sides. So it cancels there, but here we get 24. And on this side, we have 2x. Well, again, 2x cannot be the same thing as 2x plus 24. We can't add 24 to something and have it be the same thing. That violates our additive identity property, if you remember back to sort of the beginning of the semester. So, keep solving it. We know things are wrong, but let's keep seeing what we can get out of this. So subtract 2x from both sides. That cancels there. It also cancels there, giving us 0 equals 24. Well, that absolutely cannot be the case. We cannot have 0 be equal to 24. They're not the same number. So again, this is a contradiction. So a contradiction is sort of like the opposite of an identity. In an identity, it didn't matter what we plugged in for x, anything would work. You know, here though, it doesn't matter what we plug in for x, nothing will work. So the solution that we would say here is that x is equal to an empty set, or null. This 0 with a slash through it symbol, null. So there are no solutions for x. Nothing that we plug in here for x will make this work. And so again, like an identity helps us see things that are related. It helps us see if two things are really the same thing. A contradiction will help us see if two things are not related, if there's something wrong there. And again, this helps us with proofs. Sometimes we need to prove that something cannot be equal to another thing, and the contradiction will show us that, yeah, indeed, it is not equal and never will be equal. Conditionals, like I said, they're just sometimes it'll be true. We just have to have the right number in there for it to be true. Okay, so conditionals, identities, and contradictions. These are our three types of equations. So, any questions? Again, I'll allow some time for us to have questions. Okay, I don't see any questions, so I will go ahead and move on. So, last thing I want to talk about today. We've seen that we can solve equations. However, what we can also do is we can rearrange equations to say different things. And it also helps us understand what's going on in some real world applications if we do that. So, one of the most basic ways to see this is with a very, very important and useful equation that is velocity v equals distance d over time t. So velocity equals distance divided by time. Okay, and that makes sense. If you think about the speedometer on your car, it measures your speed, your velocity, in miles per hour. That is literally miles divided by hours, distance divided by time. However, we can actually rearrange this equation to say different things besides just velocity equals distance over time. So if I wanted to know what, I don't know, distance equals, what I would do is I'd want to get distance by itself. So I need to do the opposite to get it by itself. Right now I'm dividing it by time, so the opposite of that is to multiply it by time. So again, I have to do that to the other side as well to keep balance. These are canceled. We just have d left on this side. And that equals velocity times time. So if you want to know how far you have gone, take the speed that you traveled, multiply it by the time that you traveled at that speed, and it gives you the distance that you've traveled. Pretty simple. We can solve for time as well. So let me rewrite this equation. Velocity equals distance over time. This time, let's solve for d. Let's solve for t. Let's get t by itself. Now, this one's a little bit tricky. What's the opposite of d over t? How do we get t by itself here? Well, I can't multiply by d. If I multiply by d, I just get d squared over t. So I'm going to have to do something a little bit strange here. Just bear with me. I am, again, going to multiply by t. And the reason I'm going to do that is because it's the fraction that's giving me trouble here. I want to get rid of that fraction. So t cancels there. We are left with velocity times time equals d. Now we don't have a fraction, though, and we can get t by itself by dividing by time. I'm dividing by v, velocity. So that cancels. We are left with t equals distance divided by velocity. So if you want to know the time that it took for you to go a certain distance at a certain speed, you take your distance that you covered, divide it by the speed that you traveled at, and you get the amount of time that it took to travel that distance. So again, we can manipulate equations to say many, many different things. You know, it's all the same equation. This is all velocity equals distance over time, just rearranged to say it in a different way. And this can be useful if we want to solve certain cases in certain real-world examples. Okay. So, I'll go ahead and save that as well. Let's try another example. This is another very important equation. PV equals nRT. Okay, you might have actually seen this equation before. So what is this equation? This is the ideal gas law. If you probably took physics in high school and you might have seen this equation. It basically helps us understand the relationship between volume and pressure and temperature. So we have pressure, volume, temperature, okay? Now, R is the what we call ideal gas constant. It's a constant number. And N, let's see what N is. Well, if we want to understand what N is, we probably want to rearrange this equation so it says a different thing. We want to get N by itself so we can understand what it probably is. So how do we do that? Well, right now, N is being multiplied by R and T. And we could divide it by r, figure out what that is, and then divide it by t and figure out what that is. But because these are both using the same operation, they're both multiplying, we can actually do it in one step. We don't have to take multiple steps to do this if they're all the same operation. So, since it's n times r times t, we can divide this by rt. Okay, so that's going to cancel r and t. Over here we have pressure times volume divided by r times t equals n. Okay, so what does this say now? Well, this says pressure times volume divided by the constant times temperature equals n. So this is basically saying that we can figure out the amount of gas inside of something, and that is n. So if we have, I don't know, a steam engine, we can look at the pressure inside of one of the valves, the volume of the valve, and the temperature inside of that valve. Use the ideal gas constant and tell how much steam we have inside of that valve. But again, this is basically just we can make things say whatever we want them to say. We can understand these equations better if we rearrange them to say specific things. And it really doesn't matter what equation we have. We can do it with any equation out there. One that's pretty popular, you've definitely heard of this one before. E equals mc squared, where E is energy, m is mass, and c is the speed of light in a vacuum. Okay, well, what if we want to know the mass of whatever we're measuring? Okay, well, divide by c squared. And we get that m equals energy divided by the speed of light squared. What if instead we want to know the speed of light in a vacuum? Well, we take mass from this side. We get E over m equals c squared. And remember, the opposite of squaring something is taking a square root. So we will take the square root of both sides here in order to get that. And we get that the speed of light in a vacuum, c, is equal to the square root of E divided by mass. So it does not matter what kind of equation you are working with, it will always have the ability to be rearranged to say new things. And keep that in mind, because it's actually a very useful skill to have, to be able to look at these things, rearrange them, and say what you want them to say. So once again, I will allow for some time for some questions. Okay, I do not see any questions coming up. So, it is now 10:51 on my side. It has been time, so that is it for class today. When we come back on Wednesday, we will be continuing this idea. However, we will be using not equations, but inequalities. So before we go, let me show you what I mean. So an equation, like we've said, is something like 2x plus 7, plus 7 equals 4. So this shows exact balance. These are two exactly equal things, hopefully. And inequality is where we might have something like 2x plus 7 is greater than 4. So this doesn't show balance anymore. This does something different. This shows weight. So this side, greater than, means that this side is more heavy. It has more weight than this side. And that's going to have some interesting implications for our solutions then. So keep that in mind. Again, Wednesday we'll be covering these inequalities, and I will see you then. I hope you have a good day, and keep safe during this interesting time. Make sure you wash your hands. Only go out if you absolutely need to. And just stay home and keep watching these videos. Goodbye for now.